The first talk is Matthew Parkinson. Thank you.
Bless you. Is it just this microphone? Okay. So, thank you very much for the invitation. I feel very kind of not quite the right person to be here. I don't really do weak memory models. I did sit in an office next to Peter Sewell for a long time before I joined Microsoft. So I got exposed to a lot of weak memory models. And over the last 13 years at Microsoft, I've read a lot of code. John was slightly wrong in the introduction. It's not about the code I've written. It's about the code I've read that I'm going to talk about today, because I wouldn't have written these things. So the main experience I'm going to talk about is this project Snowflake that I did along 2017 was when we published, so like 2 years before and a year after that the kind of project was running. And it was about taking .NET runtime, adding manual memory management to it, so using reference counting integrated with GC, lots of kind of cool, fun stuff. And I've read a lot of the .NET runtime code to actually be able to modify it, and I read, oh, yeah. So yeah, I read a lot of actual .NET system services as well, and kind of went through lots of code. So this talk is kind of 3 nuggets that I found there. And as John asked for interaction, that's a very good idea. This talk gets worse as it goes. It's like a newspaper article. You don't really want to get to the end, so you want to stop me before. And it won't fill the time if you don't ask questions. So please do. So I'm going to start with my new best friend, flush process write buffers. So this is a Windows API call, which I didn't know at all about, and I'd sort of done concurrent programming stuff academically, but I found this in the .NET runtime. And it was kind of deep in this thing called thread suspend. So this is the thing that tears, you've got the GC running, and it wants to stop all the threads running, and it wants to know that there's no one doing mutation to the heap graph, and it's kind of getting you into that state. But there's a lot of places where you jump in and out of what's going on in the runtime, so it has to be very efficient. So it uses this thing called flush process write buffers. So I went and read the docs. So this flushes the write queue of each processor that's running a thread of a current process. So it does an IPI everywhere, and runs basically like CPU ID or like a strong fence everywhere, and then waits for them to all respond, which sounds expensive, but if you're stopping the world to do a GC, then there's quite a lot of expense going on anyway. So why would you use something like this? So the code that I found that used this was basically doing the following. So you've got one thread. Does my mouse work if I show it on here? Laser pointer. So one thread, this is the mutator, is going to say, don't do GC. Oh, Paul, yes?
Should there be a call that prevents the compilers from reordering something somewhere?
My slides develop. So please, thank you. Thank you for interrupting. Please carry on. So yes, there's going to be more put in. So one thread's going to disable the GC. Then it will check if the GC is there and wait. If it isn't, then it can modify the heap. And then it will re-enable the GC. So there's basically sort of steps in and out of like jittered code and runtime code. And some places we really can't afford to have the heap mutate. Meanwhile, you might have the GC code, so it starts by saying GC in progress, and then wait for everyone to go, and then do the GC, and then say the GC's not in progress. So this is sort of like a bit like a semaphore, but you're sort of doing one thread's notifying all the other threads that the GC is happening, and the other threads each have a sort of way of saying that they want it to stop. Yep.
Won't this deadlock, like just the code on the screen?
So wait for GC actually then unsets the disabled GC flag, and if
Just want to make
yeah, yeah. So yeah. Sorry, there's a lot of code that I read. I tried to fit it on the slide, which is yeah. But yes, it doesn't deadlock because this waits. So this is a write read. So going to my classic understanding of memory models from the neighbor from the computer lab when I was there. So I should put a M fence on both sides to make this work. So that would, on x86, prevent the reads floating above the write, and everything would be good. But the problem is that this code on this side happens a lot, and that's very expensive. And this code on this side doesn't happen very much at all. So if you can do something asymmetric, life is better. So what you have is that gone? In the code is it does flush process write buffers on this side, and it doesn't actually have stood atomic signal fence because it wasn't written in that style of thing, but it's basically, some of it was written in assembly language, some of it had a Windows thing in there, some of it was just lucky, I think, that says that this code can't be reordered. And it happens that if you do this, and you think about it really hard, and you're hopefully right, this is safe too. So the read-write reordering here doesn't happen. So if you think about what's kind of going on, the flush process write buffer is an IPI. So it's going to send an interrupt somewhere. So let's think about where that interrupt lands. So if the interrupt over here lands before the write, well, it's going to see the GC in progress when it gets to here, so it's going to go off onto wait for GC, unset stuff, and be fine. Oh, have I got really bad animations going on? Sorry, I didn't do my animations very well here. So if it lands kind of in the middle, you're still going to see GC in progress here, so that thread's going to back out. It might see the disabled GC to start with, but it will keep spinning for a little while. And this isn't just actually a spin, it does something cleverer, but sorry. And then if it lands afterwards, well, you're guaranteed that this thread will have seen the disabled GC because all of its stuff will be visible to it. So you've basically built sequential reasoning back. Awesome, I like sequential reasoning, sorry. We've got this kind of sequential reasoning back with a really expensive instruction in one side and basically nothing on the other side. And this isn't the only place it occurs, so it's used quite a few places in .NET runtime. So Linux kernel has sysmem barrier now, and that can be used for user space RCU, and Paul's at the back who can probably correct me on anything I say there, but
You're fine.
it's also, I believe, used in places in Meta's Folly library, which I think there's people in the audience who can correct me if I'm wrong there, but we have a really simple example in some code I've written, but just as an asymmetric lock where you can basically have one side of one side of a lock is really cheap and the other side is really expensive, and you can use that for as a primitive to build all this stuff on top of. It's just kind of quite useful. So to me, this is really awesome, but it's quite far from a lot of the memory model stuff because it's involving interrupts and kind of interacting the memory model with the interrupts, and there's hands. Yeah.
Yeah, I was just going to say there's also a proposal floating through the C++ community, the asymmetric fence. I forget what its status is at the moment.
Yeah, I found so David Goldblatt, I think, has put a proposal into the C++ standard for this. Yeah, I couldn't work out what its status was from what I found online. So
I'm not at all sure. I think it may be on its way into a technical specification, but there's some
okay.
procedural issues there.
Okay, Paul.
It is on its way into a technical specification, and we're going back and forth with ISO about the exact format of PS must have because they changed their mind. And it's been much. So they give up and just say put it in the IS, but they'll start it over and like that sometimes.
Okay, for anyone online listening, that there is a technical spec in C++ and it's making its way through. So I found this. So this code, if I was in a positive mood when I responded to John about the talk title, it would have been probably a love letter to flush process write buffers as the title of the talk. But actually I was in a negative mood at the time, so I was gave a negative title. so I've actually been going around telling lots of people about this and this pattern, and it's like really good. And I actually was talking to some people on one of the Windows components and using this in a place where they were currently having kind of an expensive lock that was on a fast path, and they got rid of it. And then I went to review the code, and they'd done something extra, which I was kind of shocked at. So they had basically this kind of write. So they did a bunch of stuff, and then they wanted to say that it was finished. And on the other side, they had a read. And they had a bunch of checking that things were sort of available, and then they should be able to read it. So it's sort of the exit part of a lock. And they did the flush process write buffers here and the signal fence here. And this meant that the code actually didn't require acquire release atomics, which I thought it did. It required only relaxed. And I blew my mind, and I'm still not sure I'm convinced. And I tried running it through TSAN, and TSAN didn't agree. But so anyone in the audience who wants to go through this in much more detail with me, I would really love to. So, Mark.
When you experience something like this that is like off menu, as it were, does it get tested rigorously?
Yes.
Define rigorous.
It will go into production rings, and we'll see what crashes. So I did go through very carefully, trying to work out where interrupts could land, what could go on, and yeah, so I'm fairly convinced it's right, but how this interacts with the ARM memory model, which is why they wanted to use relaxed atomics, I'm not an expert on that at all, so that would be interesting. So that was the first sort of piece of stuff. How am I doing for time?
It's 21 minutes past, so you've got another 9 minutes.
Okay, cool. Then stop me, because yeah, go.
Just to comment that this asymmetry that you talk about, where you got one efficient thread and one slower thread, it reminds me a little bit of what I've seen in GPU programming, where you've sometimes got threads doing memory accesses that are only visible within their compute unit, or some small part of the GPU, and then you want, and then the other thread, which might be in a different part of the GPU, wants to be able to communicate, and that other part is able to kind of upgrade the accesses that were made kind of quietly in one part of the GPU so that they become visible throughout the whole GPU. And so it just reminds me a little bit of this flush process write buffers.
Yeah, maybe. Cool. Okay. So.
You know, I'll bite. I didn't sleep enough this morning, but this is write to read. Why isn't it just a cheap write floating fence between the two writes to make the reads work out?
So if it was, so I think they wanted to put no fences on this code because this is really very fast path, so they wanted to use relaxed atomics only. But
The fence between the writes is pretty much a store, and it just floats down the store pipe. It's not expensive. There's no ACK. There's no.
Actually, sorry.
I mean, it seems like overkill, and it seems like it would be slower.
Does ARM have that kind of fence? Does it have a write only stuff?
Everybody's got, hell, ARM had write before I had write.
Okay. You're the memory model expert. I just read code.
Yeah. Do the math here. Okay.
Yeah. Cool. I'll go and feed back to the guy and see what he says. Peter.
What do you know about what performance testing the authors of this stuff do?
So for this piece, I have no clue. For the original .NET stuff, they did a lot of performance testing for the transition in and out of C++ code that was mutating the heap into the jittered code. And there was a very noticeable slowdown just having the M fence, basically having that fence in there, because there were a lot of little runtime functions which had to not allow a GC during, and it was C++ code, so they couldn't do anything inside that little stub function. So all of those little places that are like really cheap transitions becomes concurrent, expensive thing.
And that's visible in the whole physical performance.
Yes.
I can believe that for the first
Yeah, I don't know as this part was tested. They were mostly just wanted to just write relaxed atomics, I think. But I think it's probably because they didn't want to acquire a release, which is what we'd written in the prototype for them, and they wanted to put relaxed, but putting a fence, as Derek says, might be a better choice. Gil?
Can you use non-atomic rights instead of relaxed rights? Is there any race on the relaxed rights?
I think there is races. There's probably races everywhere. There's always races. This is basically implementing kind of a lock pattern, but for a particular operation that's going on.
But when you relaxed rights, that part, so several threads can concurrently write to the same location, and then this guy wants to read the relaxed stuff. Whatever. Somehow, if there is a race, you don't kind of.
Actually, some of these might not need to be relaxed. I think it was.
That part I can see, but the previous part, you somehow with all the relaxed stuff. Usually, you don't expect some two threads concurrently write to the same location, so somehow it's.
Yeah, I think it was actually the reads were relaxed, but sorry, I haven't got the code stamped in my brain. Okay. So I'm in 15 minutes now. I've got 2 more examples to go through, so we're doing great on time. But I didn't want to go through them all anyway. So updating running code. This is another thing I found with a .NET runtime, which I'm just going to go through quickly to scare people, I think. So one thing I found when I was reading the code was there's this thing called a JIT fast write barrier, which has in it this lovely bit where it says move absolute into RAX, this constant. And there's a bunch of alignment stuff and patch labels, and they just write into the instruction stream where this thing is, overwriting what the write barrier says. So then there's some stuff about finding the patch locations for these things, and then you update the ephemeral write barrier with these things. But there are some cases where they do this while the write barrier is still running, which, yeah. I think pardon?
Works great on x86.
Well, so they updated the code to work on ARM. So I'm, yeah. So there's a bit where it does some flush write barrier instruction cache, and then there's another flush process write buffers here because actually they're updating 2 things in the instruction stream, and they want to make sure the instruction stream gets updated in the right order. So if you have relaxed updates to the instruction stream, then it goes really horrible. So anyone who wants, I can send you all links to this code. It's all publicly available on GitHub. And yeah, you can sleep as well as I do. So any hands?
There's actually been a lot of discussion, especially on the list 5 case, about how to do this. Derek, I guess something comment on this. It wasn't the same discussion. But I mean, in general, the architectures even x86 imposes severe restrictions on updating code. You need to generally run something on the executing side before you can safely execute the code.
Yeah, I think that's what this instruction, the system call here is doing, is going off.
But usually, you actually need to do this on every thread that can potentially execute it.
I think this one's an IPI as well.
Oh, okay, so it doesn't need
But so I'm a little bit confused because when I was reading the code to do this talk, it had changed since I last read it, which, but that was like probably a good thing. But this work item here was an x86 bug, which is now under an ARM if-def. So, Paul?
Been having some fun with this kind of thing on Link as well. So I think it's a very interesting.
Yeah. At least when I read the code the first time, you had to do a flush process write buffers to get the CPU ID to execute on every other core to get the code to be guaranteed visible in some way.
You have to drain the post-cache.
Yeah. Peter.
So supposedly, over their model should now cover all the things that you're talking about, I think.
Awesome.
So
come talk to me.
Yeah. Cool. Excellent. That's good. Are you gonna tell me about it later?
Yeah.
Cool.
We
which leads me to my question here. Have you been able to extract sort of the litmus test inside of this? Like,
I've got slides. That's about a litmus test, right? No, I haven't, but I will happily work with people to do that.
I'm interested.
Yeah. So I think I'm at like time now. I have one more example, but I'll skip that. So.
Well, there's probably a good link between what you just said and the final two talks of the day, I think, about the system level. So that's probably kind of a neat.
Cool. So you put me in the wrong place, but we could read. Cool. Yeah, so that was just some things. Hope they were interesting.